Alright, we've got Lab 3 that we're beginning, which is super exciting because that means we're now beginning to work on the laser tag, which will, continue through your junior core and culminate in 390. So some documents are on the content portion of Learning Suite. There's a laser tag overview, and obviously the Lab 3 document is really important to read through as well. First of all, this is the box that the laser tag equipment will rest in. So you can see here it says Zybo. This is your Zybo board. Over here is where your analog stuff will be. So here's where your transmitter board will go and connect, and this is where the PCB will be for your receiver board. There are some other things that we'll talk about on this board here. So this ribbon connector connects your analog, the interface to your analog and your digital. Now we're going to zoom in on the analog and interface and look at that a little more closely. So from the inside of the box, this will be the connector for your transmitter board, and this will be for the receiver board. I can't handle that T, that was not a T. There we go. So we'll be plugging into those connectors on the inside of the box. And on the outside of the box, this is where you will plug in the gun, make the connection for that. And then later in Lab 5, this is where you will plug in, there's a connector on the gun for the receiver board portion of it for the photodiode. And when you use it, you want to make sure this is on and see that the LED is going. Okay, this is a block diagram. So the thing we just looked at, namely the analog portion, these two connectors are going to be the same as these orange boxes. So these orange boxes are your boards. So this is your transmitter board, and this will be your receiver board. So today we'll talk about the transmitter board, and you're going to be connecting to the Zybo, and then this will be connecting over here to the gun. That's where these lines are going to. So your gun will have a 5-volt power line to it, and it'll have a black line connecting to the transmitter, and a green line connecting to the hit indicator, and a yellow line connecting to the trigger. So we have 3 distinct circuits happening on this transmitter board that all help us during the transmit phase. So when we get an input here on this line, that is when we want to shoot. So first of all, I'm going to say what doesn't happen. It doesn't happen where when we press the trigger that we shoot. What happens when we press the trigger is we tell the Zybo that we want to shoot, and then a square wave will come back from the Zybo that will have the right frequency depending on which channel we're shooting on. So the Zybo will tell us when we're shooting, and it'll give us that square wave, and then we want to turn on our shooting LED. Then when the hit indicator comes on, it will be connected to an LED up here, and we need to turn that on. And then this will be a trigger circuit. So these 3 circuits are what you'll be making. And when we do that, there are specifications we need to meet. So this over here is our function generator. So in 340, we'll often mimic the Zybo with the function generator. The green dotted lines will be example of things on your transmitter board, and then up here, these are the things that would be on your gun. So for your transmitter and hit indicator circuit, they will both have the same basic schematic, where we have an NPN, we'll have a resistor in the base, we'll have a small resistor in the emitter for measuring current, and then you can put these on your breadboard, but then later when you test it with the gun, you will make this connection right here to the gun, and then the 5 volts and the LED will be on the gun itself. So your input from the Zybo is going to be a square wave where you want your low to be 0 and then your high to be 3.3. There we go. Beautiful square wave, just like that. This is pretty important right here. This is kind of the whole purpose of this circuit. Our input has to be less than 10 milliamps because the Zybo cannot drive more than 10 milliamps. So that's why we need a circuit in the first place. this NPN will be acting as a current amplifier so that we can provide the amount of current we need. So for our hit indicator and our transmitter, we have different needs. Our transmitter, we want to have a lot of current because we want to be able to shoot someone from across the room. Our hit indicator, we don't need as much current. We just need to turn it on. So they'll have different current specs, and this 10%, there's a little bit more room than 10% since there is some variation among the guns, but we'll be shooting for about 100 milliamps. So they will both have the same framework. You'll have different values of RB that you will be choosing to create these different current values. But they'll both have a square wave, as we said, from 0 to 3.3. They will both have a 5-volt supply, and we want them both to have less than 10 milliamps coming in to that base of the transistor. In LTspice, at the end of this video, we're going to jump over to LTspice, and I'll show you a couple things about how to get the appropriate components to do this. So we'll talk more about that in a minute. Okay, so that was box 1 and 2 of our block diagram. The third one was our trigger circuit. So let's go back on our block diagram and take a look at that. So what we want on this trigger is that when we pull the trigger, what's happening is this line will be high. It's going to be 5 volts. When we are not pulling the trigger, it's going to just be floating. It's going to be nothing. It's going to be an open switch. And what we want to be giving to the Zybo is when we're not pulling the trigger, we want to give it 0. And if we're pulling the trigger, we want to give it 3.3. So what we need to do is figure out how to do that. And it's really common in electronics to have what we call pull down resistors and also pull up resistors. So if we look at this right here, our diagram on the left, we have a floating node if this switch is open. And a floating node is not something that digital circuitry likes because they want a 0 or a 1, and this is unclear what it would be if that switch is open. So what we do is we add a pull down resistor that we can see here. So now if our switch is open, there's no current flowing in this branch, so that means it's 0 volts here, it's 0 volts here, and I do not have a floating node anymore. I have a low. And then when the switch is closed, then I have my VCC coming through and I have a high or a 1. Similarly, you could do the same thing with a pull up resistor. If I had a switch where I have something like this and it connects to ground, and then here's where it's going to my digital, I can go through a resistor up to, VCC or whatever, right there. And this would be a pull up resistor that would hold this line high unless my switch is closed. So pull down and pull up resistors are helpful. We don't want floating nodes. So let's look again at what we want. So right now, here's our trigger output. So coming from the gun, if my trigger is open, I've got floating, which I don't want, so we'll correct that. If my trigger is pulled, that yellow wire from the gun is going to have 5 volts on it. Then let's think about what we want to provide to the Zybo. When the trigger is open, we want to provide 0. When the trigger is pulled, we want to provide 3.3 volts. So yours is going to be a little bit different than just a typical pull down resistor, because when your trigger is pulled, you want to be able to switch it from 5 volts down to 3.3. So we can see right here our right answers. Here is the pinout for your circuit. Now, this is a good example of, for example, in industry, if you had a job, projects are never just one person. There's usually a big system and someone might have a portion of a project. So even though this project is all you, there's still a system because there's already some things that are determined. For example, if you look on this board, for example, this pinout, it's already determined. And so we would know which channels are which on that ribbon connector to the Zybo. So we need to work within that framework. So here's the pinout that's been given. and you'll have a connector you'll be connecting, and it's really important to, from the start, think through what is going on where. So you can either do this in your schematic, where you could come back here a couple slides and you could say, for example, on my transmitter, these are totally false, but let's just make it up. We could say, okay, pin 1 needs to go to my gun, pin 2 is from my Zybo, and then over here, this was for my transmitter. So on my hit indicator, I could say, oh, that's pin 4, and you just want to be thinking through these things. So you can either do this by drawing the picture on a schematic, or another way to do it would be, I made these little vector board things. You can see that it mimics the real vector board. So you could say, oh, okay, well, I'm going to, look over here. It says pin 1 is ground. So I could just, have something over here. I'm connecting some of these to ground. And then I'd say pin 2 is my transmitter digital signal, and then pin 3 is my black wire and gun. So, I could draw, oh, I need to do a resistor from here to here, and just really think through which pin is which. And that's really smart. So you're kind of thinking through these before you solder, so you don't make a mistake. It's a lot easier to think through it and then just solder once instead of having to redo it. Another note on soldering here is it's really nice when you're using a vector board to use the leads of your components to connect. So if I have, this resistor here on a board and then there's leads, I poke my leads through the hole, but then on the back of the board, pretend this is the back where those leads came through, I can just use my lead to connect to the other device, and then this lead over here could go connected over here. And I can use the leads themselves to make my connections. Is the best way to do that on your vector board. So basically you're going to use this table and you're going to think through everything and think, okay, this is coming from my Zybo, oh, this one's going to my gun, and just really think through so you can be confident that when you create this transmitter board, that it'll work great. And here's a little bit of an aside, but this is a very logical question that a lot of 340 students often ask. In 390, how it has been going the last few semesters is Dr. Hutchings will assign you a lab partner. So it will likely not be the lab partner you had in 340, and you only need, one board. Again, each of you need a transmitter board, and each of you need a receiver board. So hopefully it'll work out where you guys are assigned and you'll just, use that board. But the answer is you only need to be doing one transmitter board for your partnership for 340, and then in 390, often it just ends up evening out. Occasionally someone might have to build a new board, but they can just copy the components they already have. So one board per partnership is sufficient. Okay, when you're soldering, please use good soldering practice. This kind of tip would be awful. You need to clean that, flow some solder on it, scrape off the excess. You want a bright, shiny tip. It gives you much, much better heat transfer. You want to bring your solder down and not touch it to your tip. You want to touch it from the other side from where you're soldering. So you would put the soldering iron here, and you'd want to be making contact with the lead and making contact with the pad. Then you touch the solder to it, the solder will hopefully start flowing. Then you remove the solder from it, and then shortly after, pull your soldering iron out. You want to have a nice convex area of solder that's smooth and that it's shiny. Then you can know you have a really good connection, and then that will give you a good electrical connection and a good physical connection. And on this lab, we will be checking your solder joints. Please make them awesome. Also, when you're doing this lab, please take turns. Let both lab partners have a turn soldering. Let both lab partners do part of the LTspice. Let both lab partners do, part of the building on the breadboard and testing. Okay, so you're going to be designing 3 circuits. You're going to be simulating them in LTspice, making sure they check, pass all the specifications. On LTspice, since we're working now with BJTs, please expect what happens in LTspice to be different than what happens on your breadboard, because there's beta for these BJTs and it has a pretty wide range. It can be from 50 to 100 up to 300 or 400. So since when you're doing it, you don't know your beta value, you're going to do it in LTspice and you're going to pay attention. So I'm going to come back a couple slides back to our circuit here. So in this circuit, really, we're only having you design one thing. We're telling you put a 1 ohm resistor here, we're telling you use a BJT, and really this is the only guy you're picking. So you're going to design and pick this, and you're going to use LTspice to design it in whatever manner you choose, doing a parameter sweep or however you'd like to do it. So we're not doing this so then you'll know exactly the right value when you go on the bench, but it still is helpful because you can say, oh, hopefully from the equations you get a feel for this, but you definitely see in LTspice, if I increase RB, well, what happens? Does my current decrease or increase? And you can see that relationship. Then when you get on the bench, if you don't have sufficient current, you'll know which direction to shift your RB, or if you have too much current, you'll know which direction to shift your RB. So you're going to be picking those resistors in the base, and then you'll be checking it on your board, and hopefully you can get it right. But again, adjust that expectation that it's going to vary. So once you've designed all 3 of your circuits and you've simulated them in LTspice and they meet your specifications, you'll want to save those results for your report, and often it's helpful to have plots and schematics from LTspice in your report. Please have white backgrounds on those. Then you're going to build all your circuits and you're going to modify them on your breadboard until they meet specifications. At this stage, it's very helpful to check with the gun because the gun has a little bit different LED than the one in your kit, and you want to make sure it will meet specifications with your gun. We'll have guns in the lab for you. At this point, when it's working well, you are ready to lay out and solder onto the vector board. Once you've done that and you're content that it's meeting all your specifications, you can pass off the transmitter board with the TA. That will be due by the end of your lab section, whether it's on Wednesday or Thursday, that first week of October, and then the following week, the night before your lab section, is when your lab report will be due. So that's a good lot of information on the lab, and I want to show you a couple things really quick in LTspice in case you're not aware of this. So here I started building my circuit. If I want a square wave, since that's what our Zyba will be giving us, I can come in here and I can select pulse. So you're going to have a value. Let's say I want to use 0, and then I could say 3.3. Now this is the part I want you guys to know about. You're going to have, if there's a delay or a rise and a fall, these are for, non-ideal square waves, which we're not caring too much about that. But the part that we do care about is this right here. We have a T on in seconds and a T period. So if I have a period, let's say I have a period of 1 millisecond, I can write that. Now the T on is going to be what portion of that period I want my signal to be high. So if I say 0.5 milliseconds, then I'm going to have a 50% duty cycle on my square wave. Half the time it will be high, half the time it will be low. If I say, 0.2, then I'm going to have 20% high, 80% low. So just remember you have your period, and then you're going to say what portion of that period you want it to be on. All right, now I've got my pulse in here. Now I need a BJT. So I'm going to come over here to my components. I'm going to say NPN, and I'm going to place it. All right, here we go. That's just lovely. Now I'll wire it in. Oops, wrong button. F3, and I'll connect it up. Now the cool thing is I can go over here. I'm going to right click here where it says NPN. That wasn't right. I'm going to right click on the component itself. That's better. Okay, so we right click on the component and I'm going to click pick new transistor. Now I can come over here and pick my actual transistors that we have in our kit. So they're the 2N3904. Okay, and perfect. So that's the one we have in our kit. And I did that wrong because I did not give myself a spot for my LED. So let's get rid of that. All right, let's grab an LED. Now we do not have the LEDs in our kit in LTspice. So I'm going to, oh, that is not where I wanted it. That's okay, I'll move it. So if you want to, you could come in here and you could say pick new diode, and you could look through these and you could say, well, you know, here's my specs, and we have a series resistance, which hopefully now you guys know more about series resistance from our last lab. We have a saturation current. Those are always really small. All a saturation current means is the current that still flows through even when it's off. So we've got Schottky diodes and Zener diodes. So if you're picking one, you'd want to come down and find an LED and, you know, just, I don't really bother. I just pick one and I say LTspice is not actually going to match super close to my board, but this will give me a pretty good idea. I know that LEDs have a curve, and I kind of know what that curve looks like because we did it in lab 2, and so I'm okay with that. All right, so I've got my 5-volt supply hooked up to my LED, I've got my NPN, I've got my square wave, and then I put a 1 ohm resistor here, so now I could just be simulating and trying to figure out what value I want here on my base. So I could pick a value, run it, and then adjust. And my hit indicator I want under 20 milliamps, and my transmitter I want about 100 milliamps. And that is really cool. If I wanted to go beyond that and be more specific, there are ways where you can actually come in to this right here. See this model information? Where it has all this information. This is what LTspice uses when it's looking at that NPN. So in lab 5 we'll actually do this, where we can go in and we can sweep a parameter of the model and say, oh, well, let's take our beta. Maybe our beta on our transistor is 50, or maybe it's 100, or maybe it's 100, or 200, or 300, and we can sweep through those values and we can see how our circuit would perform at each of those values. That's not very critical for today, but it's a possibility with LTspice. There's all kinds of cool things like that. So this is what I wanted to show you. Now hopefully you know how to get started with your lab 3 and pick the components and get it going in LTspice. Please make sure on your lab report to have it be really clear, have it be really easy to read. Show us that you met your specs in LTspice. Show us that you met all the specifications for the 3 circuits once they were built, and I hope you guys have a good time. I feel like this lab is fun. You get to sink your teeth into a couple different things, you know, some design and some testing and some soldering, and then you'll be using it also in 390. So good luck, and I hope it goes great.